welcome back. And today that floppy drive is going to work, I promise. And well, you actually already know this because you saw the thumbnail. And if I'm being honest, I actually already know this because I film things out of order. That's just how it goes. So I promise you're gonna see some very cool stuff with that floppy drive today. But before we get into that, I wanna talk briefly about why I've spent so much time working on the floppy. Because initially I bought it just to test out the FFC card to give us access to the Finch drive so we can get the data off of it. But here we are, like part 6 or something, deep into trying to get this floppy drive going. And wow, why am I so obsessed with this drive? And well, it all comes down to how I want to build out the system. A couple of episodes back, I received the counterfeit system, and I was really excited about it because it had a Hawk drive. And actually, the Hawk drive that came out of that is currently sitting in our main system now, and that's what's got us to the point that we've gotten to today. Well, I didn't quite like how the counterfeit system cabinet or chassis looked, and I was maybe thinking about pulling all the insides out of it and transferring it over to the second genuine cabinet that I have. And the backlash from that idea was real. You guys did not like the idea of not building out the counterfeit system because, well, there is a bit of history attached to the counterfeit system. Granted, I can't prove any of it. There is no documentation or provenance that we can show that this was a genuine counterfeit system. But I mean, the history's there, and you know what? I think you guys are right. It should be built out. And I think that's what I'm going to do with it. I'm going to build up that counterfeit system as a proper counterfeit system. Now, I am going to change it to a single Hawk system. And that's because I want to build out the primary system, the one that we're working on right now, to be a top tier, fully spec'd out machine. And in order to do that, well, I want to put pretty much every drive type that I have at my disposal into it. So I actually made a little render here in the Windows 3D Builder software. And you may notice that the primary cabinet here has two little black boxes sitting above the Hawk drive. And that's where I want to put a floppy drive and a Finch drive. And then in the second genuine cabinet, I want to put another Hawk drive and the Phoenix drive. Now the Phoenix drive is broken. Well, the other Hawk drive and the Phoenix drive are both broken. Now I'm really confident that we can get the Hawk drive back up and going with no problems, but the Phoenix drive is going to prove to be a much more difficult challenge. And I think we have a plan on how to move forward with it, but that's something that we'll tackle pretty far in the future. And then the third counterfeit system will get the third Hawk drive, which is in incredibly rough shape, but I've become well versed enough in the Hawk drive that I am starting to gain enough confidence to think that maybe we can get all three of these Hawk drives up and going again. And so that is our current roadmap for the Centurion hardware that I have. And that's what we're working towards. And that's why I've spent so much effort trying to get this floppy drive to work. And like I said, it is working. So let's hop over to the bench, and I want to walk you guys through the insane journey that it was to get it to this point. In the previous episode, we left off with the difficult realization that the microcode for the FFC had been written for a different CDC 8-inch floppy drive than the one that we have here. This is a CDC 9400, and I believe the microcode was written for a 9406. They are very similar, except that the 9406 has a very different mechanism to seek the head, and that allows that drive to support seeks up to 3 milliseconds, whereas the stepper motor in this can only support seeks up to 10 milliseconds. So the FFC was sending seek pulses too quickly to our drive. Now, I, at that point, was pretty much out of it. I was dead. I had spent so much time on this, I didn't know where to go next. But SJ Software is an absolute legend and understands more of the FFC microcode than probably anyone alive today. And he helped me get the microcode updated. And well, here's the information about it. It's staggering, the work that he's done here. And essentially what we have on the far left, we have the address. This is the address that is coming into the 8 microcode ROMs, and each one of those ROMs is outputting a byte to give us a 64-bit value coming out, and that is what is listed right next to it. Now, SJ Software went through an unbelievable amount of effort following the lines of the microcode ROMs, seeing where they went based on Meisaka's wonderful schematic, and figuring out what each byte was essentially controlling. And he wrote essentially an equivalent to assembly here. Now, the most important part of the microcode that we're looking at here is that when we had the logic analyzer out and we were taking a look at the address of the microcode when we were running the seek test, we saw that it was spending the majority of its time at address 02B2. On the occasion we saw a 02B1 or a 02B3 or something like that, but it was almost always stuck at 02B2. And if we look at SJ Software's pseudo assembly here, it says that it subtracts 1 from Q, and then it says branch if Q is not 0, and it branches back to 2B2. So this is just a really tight loop. Now if we look at the address 02B1, Q is given a value of hexadecimal 64. This is 100 in decimal, which means that 02B2, that address should loop 100 times. So then if we look at 02B3, we have R03. We decrement it, and again, we go back up to 2B1, we load hex 64 into Q, and then we do our 100 loop again. And so this is a loop within a loop. It loops 30 times. And we can tell that because if we go up to the address 02B0, we are loading register 03 with the value 1E. And 1E in hexadecimal is actually 30 in decimal. That loop of 30 times is how we're getting that 3 millisecond delay. So all we have to do is change how many times it loops. We just need to change 1E to 64. And 64 is 100 in hexadecimal. So we loop 100 times within a loop of 100 times. And that slows it right on down to 10 milliseconds. That's right. All we had to change to get the microcode to work with the CDC 9400 was 1 byte. Just 1 byte. How crazy is that? It was just one value, 1E264. So that, unbelievable. I can't believe it was only one single byte that was tripping us up. Now that 1E is located on ROM H4. We can see that if we look at the 64 bits here, we can see it says 1E in the middle there. And if we just count bytes over, 00 would be ROM H1, FF is H2, 03 is H3, and then 1E is H4. So I just need to change the 8-bit value at address 02B0 in the H4 ROM. So I had to go out to the garage and I cut up an adapter board to put one of these flash ROMs that I have. I don't remember what the code on them is, but it's a simple little flash ROM. But that allowed me to essentially plug in a separate flash ROM into the FFC. And that got it seeking perfectly. We had effectively slowed it down to 10 milliseconds, and now the FFC microcode is specific to the CDC 9400. I was so confident that this was gonna solve it, so I ran the format test, ran the read test, and it didn't pass. On the low tracks, we were getting errors of like 21, which is, I think, data not found. And then on the higher tracks, once we got above about track 10, we were getting error 33, which is on the wrong track, which means it's reading enough bytes back to realize that something is amiss. And this was like the next week of my life. I just left the camera off and I probed everything. I took hundreds of scope shots looking through the entire thing. I was desperately trying to figure out what was going on. I ended up actually replacing about 8 chips on here. Some of them were definitely bad. Some of them were Hail Marys. None of them solved the problem. It just always failed the exact same. And so I was getting really pretty desperate, and I said, you know what? I don't know at this point if it's a problem with the PCB or if it's a problem with some physical aspect of the drive. So I took the drive B PCB, which was missing some chips, and I put some sockets in and I repopulated everything, and I tossed the drive B PCB in, which is what's in there right now, and suddenly it came to life. All right, I've got a fresh floppy in the drive. We'll start by just formatting it. We'll do a 06 here. I heard the head load. It is slowly stepping through and formatting the floppy now. We just gotta wait for it to finish. And there we go, the format just finished, so we'll hit space. So let's do the one that has been killing us for ever here, 09 floppy read test, and here it goes. I can hear it seeking the drive. We're getting no errors up here. This read test in particular reads every single track. This is one that SJ Software rewrote for us. So it's going through and performing a read test on every track. And if we see it say pass here on the bottom, that is going to be absolutely mega. Yes, there we go. It said pass, press space. Yes. That means it is working perfectly. Finally, thank God. It's been a long journey, but that also means that we should be able to see that disk in the operating system. So I'm going to get out of the diag test here, reset the computer, spin up the Hawk drive, and now we're just waiting for the Hawk drive to fully spin up. There we go. I heard the heads load. The ready light is on. So I'm going to press H1. It did its 3 RTZ seeks there, and now it's reading off of the Hawk drive. It's going to start loading the operating system now. Yeah, and there we go. OS 7.1-E. I'm going to hit enter here. Enter 082384. Don't care about the system time. Now it's going to finish loading the operating system, and when it says CRT 0 ready, we're now fully in the OS. So I'm going to type .sta here, and I heard the head of the floppy drive load, and check it out. It says data 6, 1 soft term. Those are our 2 platters for our Hawk drive, and then it says 2 something 0216 et 1 for the year, but that's actually not unexpected because the format test on the diag card essentially just writes, I believe, E5 to everywhere. And so E5 must be getting interpreted a little weird here. So let's actually set this floppy up as a new disk. We'll do s.new dsk, hit enter. It says enter disk number, that's going to be disk 2. Hit enter, it loaded the head, and then it says disk 2 is guarded. And again, this is not all that surprising because it just wrote E5 to everywhere, which means that whatever bit in there is a software write protect, what they call guarding. must have been set. So we need to no guard disk 2, and we can do that pretty easily by typing .noguard space 2. So let's go back and run s.newDisk again. Our disk number is going to be 2, that's our floppy. Loaded the head, enter new disk name, we'll call it Usagi, and then hit enter. Am I ready? Yes. Enter. It loaded the head, it's doing writing. Oh yeah, it's writing all sorts of new stuff. So it is doing writes on the floppy to turn it into I guess a bootable disk or a readable disk by the Centurion at the very least. All right, it says .use CRT0 for sys RDR. I think that means it's finished. Now that took about 3 minutes, maybe not quite that much, but I did some chopping there to cut out a little bit of that so you guys didn't have to just stand around and watch me patiently wait for it to do its thing. But I'll type .sta again, and I heard it load the head, and there we go, 2 Usagi. It gave it today's date, August 23rd, 1984. Let's do a .dir on drive 2 there. This is going to show us the directory listing of what's on that floppy. So we can see that there are 4 files, 3 of them use 1 track, 1 of them uses 8 sectors. So we're using 3 tracks, 8 sectors worth of data, and there are 92 tracks and 8 sectors available for us to put things. Now, counting tracks and sectors seems like a strange way to count the amount of space available. And well, the Centurion is a little strange. Everything is really based around the original storage type that Centurion was using, which was the old Sykes tape drive, which was 400 bytes per sector. But 400 bytes per sector and 16 sectors per track is how they're organizing everything internally in the Centurion system. But the floppy drive itself has only 76 physical tracks. So where are we getting the extra 20 tracks that we're seeing here? Well, since Centurion is only using 400 bytes per sector and they're sticking to 16 sectors per track, it means that they can actually put about 1.25 tracks in a single physical track on the disk. And the FFC card is doing the translation between the two. So that's an incredibly confusing way to do things, but it means that we have a ton of space available on this drive to put other interesting things. Now, what I am thinking here, maybe some of you guys are thinking the same thing, let's do a .dir1 on soft term here. Okay, so we can see that the first 4 files are pretty much the same. That's the initial program loader. But to get into the operating system, we need @sys, @load, and @osn. I think if we take those 3, they're not necessarily files, one of them is a library, but if we take those 3 items, copy them over to the floppy drive, we should be able to boot the OS from the floppy drive. We'll just start with the smallest file, @osn. And the utility to copy that is stored in the S folder, and it's called .copn. So I'll do s.copn, and I want to copy @osn, and I want to copy it from disk 1 to disk 2. I'll hit enter. It says library or new line. We're just going to do new line for no library. Hit enter again. The head loaded, and now it is copying the @osn file from the Hawk drive over to the floppy drive. I can actually hear it reading over there. And there it goes. It says input was @osn, output was @osn, and it copied it over to disk 2. So if I do .dir space 2, it should show us the directory listing of 2, and now we have @osn on there. So now we just got to copy over @load and @sys. There we go. We have @osn, @load, and @sys. @sys is using 64 tracks. So that all looks correct. We have 19 tracks available to put anything else on there that we might need to, but I don't think we need anything else to actually boot into the operating system from the floppy drive, and that's what we're going to do right now. So I'm going to push the load opsys button. That's going to get us back to the D equals prompt. Now, just to be absolutely certain that we're booting from the floppy drive, I'm actually going to turn the Hawk drive off. So it is spinning down now. It's going to get a little bit quieter in the room and hopefully a little easier to hear me. There we go, the start-stop light kicked off. The Hawk drive is completely off. The only way we can boot into the operating system now is through the floppy drive. So I'm going to type F0 here, and I'm going to hit start on my little stopwatch here, because this I think is going to take a while because floppy drives are slow. It takes about 20 seconds to boot fully into the operating system with the Hawk drive spun up. It's going to take a little longer than that with the floppy drive, so I'm going to actually time-lapse this a little bit and just let it sit here and load. So there we go, about 3 minutes and 30 seconds to boot fully into the operating system. It's slow, it's real slow, but we're in the OS. If I type .sta here, it's going to load the head, read the floppy. Now this status procedure takes a little bit longer, but there we go. 0 and 1 are the Hawk drives. They are offline, and 2 is our floppy Usagi, and we have successfully booted into the operating system using the floppy drive only. That is awesome. What a victory. What an unbelievable victory. Now, it's largely useless like this, and I'll explain why. So yes, we did actually boot into the operating system using just the floppy, but it is actually largely pretty useless. That's because the way that the Centurion is set up is a little strange. There's JCL commands, and then there's actual jobs. So JCL commands, those are the commands that you see me type in that start with just a period. So .set a dd equals 1. That is a single JCL command. But the utilities are something a little different. So when you saw me copy files over, I was doing s.copn, and then I put some arguments on the end there. That is an actual utility program that is stored in the folder S. Now the COPN file is actually just an ASCII file that is filled with JCL commands. It has a bunch of JCL commands that it runs in a row, and then finally at the end it gets to an actual executable file that it then executes from there. So without having the S folder that has all of our wonderful utilities in it, we can't actually do a whole lot. We can, however, run every single JCL command because that is baked into the operating system. And I've got a list of them here. And I think there's actually a few more that aren't on here. These are just ones that I've figured out by looking through other files on the drive. So the operating system does have some usability, but it's extremely obtuse and very difficult to use without job files already built. Those ASCII files that have all of the commands in a row that just run straight for you. Well, that's awesome that we were able to get in there, but like I said, it's largely useless. And that's not actually what I'm most excited about getting this floppy drive up and going for, because, well, that was really fun to do and kind of cool to see. What I think this is really going to help us do is actually help us troubleshoot the Finch drive, because I can copy @load and then copy the S folder and the question mark folder over to a floppy, and then I can get to the @load prompt where it says name equals. And from there I can run a lot more in-depth diagnostic programs. Like I can do question mark dot question mark Finch, and that is a dedicated Finch testing program. That is where I think this thing is really going to shine. And sure enough, we have the floppy drive working correctly and perfectly now. That is a massive, massive win. It doesn't feel like a clean win though, because the other PCB here, drive A's PCB, is still not working correctly. I actually swapped it in again when the camera was off just to see if something had changed, and nope. There's still something horrifically wrong on this that I can't figure out. So while we did get a win, it just doesn't feel like a clean win. But to quote the great Dominic Toretto, doesn't matter if you win by an inch or a mile, winning's winning. And well, now we have a working floppy drive, and that, my friends, is an epic win. And it's going to pave the way for us to work on the Finch drive, which is exactly what we're doing next. So I want to thank you guys so much for watching and joining me on this ridiculous journey to get the floppy drive going. But now that it's going, it's time to get into the really exciting stuff and find out what is wrong with the Finch drive and what kind of data is hiding out on it. So thank you guys so much for watching, and I hope to see you in the next episode.